Welcome to EPG Pathshala. In today's module, we are going to discuss on agrometeorology. The meteorological and hydrological factors are very important in the agricultural production. This gives information about the behavior of the weather elements that have direct relevance to the agriculture and their effect on crop production. So, in this module, we are going to discuss about definition and scope of agrometeorology, the microclimatic characteristics near the crop canopy and its effect. Also, the various applications of agrometeorological techniques. Agrometeorology, it is one of the branches of biometeorology and it is abbreviated form of agricultural meteorology. It is an interdisciplinary science dealing with the interactions of physical environment, that is meteorological, climatological and hydrological factors with agriculture, including the animal husbandry, horticulture and forestry, apart from our field crops, and the application of such knowledge to improve the agriculture production processes in terms of quantity or quality of produce, pest or disease control and sustainability of land and resources. It provides practical solutions for harnessing climate potential of an area and for protection against or avoidance of climate related risk. Let's see what are the scope of agrometeorology. Agrometeorology is construed as a four-pronged strategy. The first stage deals with accurate description of the physical environment and biological responses. In the second stage, the interaction of biological systems with their physical environment is studied. Agrometeorological forecasting is done in the third step, and in the fourth step, development of agrometeorological services and support systems for real-time farming system management is done. These services include providing the farmer and policy makers with strategies for long-term sustainable use of natural resources, tailor-made weather information, tactical solution and technological know-how for short-term adjustments in day-to-day agricultural operations. Agrometeorological studies extend from a upper few centimeters of active root zone in soil to few vertical meters of the atmosphere in the immediate vicinity of the soil surface, where the crops and higher organisms grow and the animals live. The scope of the subject includes the characterization of the agricultural climate for determining crop growing season and delineation of agroclimatic zones, climatic crop planning based on water requirement of crop and its availability for sustainable production, weather-based crop management practices like sowing, interculture operation, nutrient application, irrigation scheduling and harvesting, developing crop weather relationships, large area crop monitoring to check crop health and growth, simulation modeling and pre-harvest yield forecasting, extreme climatic events and their management, and also provides the agro advisory services. Let's see the microclimate near the crop and its effect. The state of the atmospheric in and around a crop surface is distinctly different from the rest of the atmosphere. The crop architecture, surface characteristics and management among other things determine the ambience and have bearing on the crop production process. The important factors that affect crop canopy are solar radiation, temperature, frost and wind. Let's see one by one in detail. Solar radiation. The solar radiation is intercepted by the crop canopy, is used instantly and cannot be stored for future. It controls the principal physiological process of plants which is responsible for economic yield, that is the photosynthesis. It also regulates the evapotranspiration and consumptive water use by the plant canopy. The angle of incidence of solar radiation, spectral composition of the radiation and the ratio of diffuse to direct radiation intensity are important factors for crop growth and yield. Let's see the energy balance of crop canopy. It can be expressed as Rn is equal to A plus Le plus S plus P plus M, where Rn is the net radiation, A is the sensible heat flux, that is around 10 to 15% of net radiation, Le denote the latent heat flux, which is around 75 to 85% of the net radiation, and P denotes the energy used in photosynthesis, which is 5 to 15% of net radiation. M is the metabolic heat and energy stored in the crop, which is around 5% of net radiation. The different components of energy balance vary with crop stage, soil moisture condition, wind speed and direction. The maximum amount of net radiation is generally used as latent heat of evaporation. During daytime, the net radiation is positive and in night it is negative. The radiation interception and distribution inside the crop canopy. About 75% of the incident solar radiation on the plant canopy is absorbed, 15% is reflected and 10% is transmitted. The plant leaf strongly absorbs in blue and red wavelength, but much less so in green. Further, it absorbs near infrared, that is NIR, only weakly but strongly in the IR region, that is infrared region. The above optical features vary with leaf type, crop species, biotic or abiotic stresses experienced by the plant canopy and moisture or organic matter content of the soil background underneath the canopy. You can see in this figure, the top figure, it is a typical spectral reflectance patterns of the leaf. You can see the leaf pigments, cell structure and water content. With respect to that, the absorption at various wavelength occurs. And you can see the chlorophyll absorption at blue, green, red wavelength, while your water absorption in the infrared region. And in the second figure, you can see the comparison of spectral reflectance pattern of soil, green vegetation and dry vegetation. The difference in optical properties of the earth objects at various spectral bands are explored through remote sensing technology for the problem solving in agriculture, such as land use, land cover mapping, in-season monitoring of sown area progress and crop health, agricultural drought, disease pest occurrence and input applications in precision farming. The remote sensing data acquired through airborne or spaceborne platforms, spectral indices, canopy reflectance models, crop simulation models, etc. are used for such purposes. The intensity and spectral distribution of radiation within the crop canopy is important as these control the plant photosynthesis and the microclimate. Such information can be used to desirably manipulate the crop environment for optimal use of sunlight and other resources as well as for the pest and disease control. The breeders can utilize such information for breeding new idiotype, that is an ideal plant model. You can see in this figure the ideal arrangement of plant leaves for efficient light distribution from 0, 10, 20, 30, 40, 50, 60, 70 and 80 degree what will be the radiation interception and distribution. A planophile, that is a plant with perfectly horizontal foliage, is photosynthetically more efficient than an erectophile, that is the plant with perfectly vertical foliage, as the relative light interception of horizontal and erect foliage is in the ratio 1:0.44. In full sunlight, generally a vertically inclined leaf can harvest light more efficiently than a horizontal leaf and the optimum inclination is 81 degree. While considering the all plant for most efficient use of light, the upper leaves in a plant canopy should have a near vertical orientation, whereas the lower foliage should be almost horizontal. An ideal arrangement of the plant canopy is for the lower 13% of the leaves to be oriented at an angle of 0 to 30 degree, the middle 37% should be at 30 to 60 degree and the upper 50% should be at 60 degree to 90 degree with the horizontal. For young plants, the percentage of light interception is smaller and also varies much throughout the day, that is minimum at noon and maximum during the morning and evening hours. Also, during sunrise and sunset, high proportion of diffuse light which is favorable to photosynthesis penetrates into the canopy. The crops sown in the north-south direction at all latitudes allows more intercepted radiation than that of east-west orientation. So, here you can see the ideal arrangement of the plant leaves for the efficient light distribution as we have already discussed in the earlier slide. As the radiation penetrates the canopy from top to bottom, its intensity gets reduced and such vertical light distribution profile is governed by Beer's law. It is I is equal to I0 e to the power minus kf, where I is the intensity of light at a particular height within the canopy. I0 is the intensity at the top, k is the light extinction coefficient of the leaf, that is the ratio between the light loss through the leaf to the light at the top. F is the leaf area index, that is LAI, and E is the base of natural log. The rate of photosynthesis and radiation use efficiency of the plant is dependent on PAR absorbed by the leaves and green tissues within the canopy. To compute the absorbed PAR, 4 types of flux density measurement represents the incoming or outgoing fluxes. These are I0, which is incident PAR at the canopy top, that is incoming one; RC, which is the PAR reflected from the canopy top, that is outgoing; TC, that is PAR transmitted through the crop canopy to the soil surface, which is also incoming; and RC, which is reflected from the soil surface, which is also outgoing. APAR is computed using the formula I0 plus RC minus TC plus R0. APAR is used to compute light, the radiation use efficiency, the light use efficiency or the radiation use efficiency. It is the ratio of amount of dry matter produced to the amount of cumulative PAR absorbed of the plants, and in simulation modeling for estimation of vegetation primary productivity, that is NPP, net primary productivity, or GPP, which is gross primary productivity. For the operational convenience of the measurement, sometimes intercepted PAR, that is IPAR, is used in lieu of APAR. IPAR is generally higher in magnitude than that of APAR. That is, all the intercepted PAR does not translate into the absorption by the plant canopy, and IPAR is equal to I0 minus TC. This RUE is higher for C4 than C3, that is radiation use efficiency is higher for the C4 plants. It is also higher in cereals than that of crops with oil and protein rich seeds. The average radiation use efficiency for a wide range of crop species was reported to be between 0.85 and 3 gram per megajoule for C3 crops and up to 4.8 gram per megajoule for C4 crops. The atmospheric factors other than the radiation that affect this radiation use efficiency include temperature, vapor pressure, and the drought. Temperature. The environmental temperature has a primary role in plant growth and its geographical distribution over the earth. In comparison to air temperature, the amplitude of variation in soil surface temperature is much more pronounced. The soil temperature largely depends on the prevailing air temperature near the surface. However, a number of factors such as aspect and slope of the land, tillage, soil texture, organic matter, and irrigation or moisture content determine the degree of difference between air and soil temperature. From the crop germination, the soil temperature is most important one. The soil temperature also affects the plant growth processes. Let us see how the high temperature affects the plant. It has direct thermal effect. The thermal death point, it is a temperature above 50 degrees Celsius may kill many annual crops. The limit varies with plants such as shade loving plants are killed at lower temperature. The other one is it affects the mineral nutrition. Absorption and subsequent assimilation of nutrients get reduced, like absorption of calcium getting reduced at 28 degrees Celsius in maize. Nutrient uptake is affected by both soil and air temperature in rice. Nitrate reductase activity decreases under high temperature. At higher temperature, even for short period, it affects the crop growth, especially in the temperate crops like wheat. The high air temperature reduces the growth of shoots and in turn reduces the root growth. The pollen development, it is affected by this high temperature, and the high temperature during booting stage results in pollen abortion. In wheat, the temperature higher than 27 degrees Celsius cause underdevelopment of anthers and loss of viability of pollen. A temperature of 30 degrees Celsius for 2 days at production deficient stage was reported to decrease grain yield of wheat by drastic reduction in the grain set. Another impact is scorching. The high temperature leads to dehydration and often leaves are scorched. The high scorching sun also causes injury to other exposed surfaces such as sun scald on the barks of the plants. The low temperature also has impact on the plants. One such effect is chilling injury. If the plants of hot climatic regions are exposed to low temperature, they will be killed or severely injured. When the night temperature is below 15 degrees Celsius for the field crops, that is especially the tropical annuals, it may show yellowing symptom. The freezing injury. The water freezes and forms ice crystals in the intercellular spaces. As on freezing, the size increases, it ruptures plant cells and leading to death. The temperate crops like potato is also very susceptible to the low temperature. Suffocation. The formation of thick cover of ice or snow on the soil surface prevents the entry of oxygen and crop suffers due to the accumulation of harmful substances. Heaving. The natural mechanical lifting of plants along with soil from its actual position by ice or crystal is known as heaving. Effect of frost on crops. Frost is a climatic hazard that causes serious damage to standing crops in temperate and subtropical climates. Frost is a weather hazard that occurs when the environmental temperature drops below the freezing point of water. It is formed through the physical processes of radiation, that is cooling due to radiation loss from the earth during calm winter nights, and advective cooling due to incursion of cold air mass. The probability of frost damage is high if the cell size of the plant is large. The winter vegetables like potato grown in northern part of India are very much susceptible to frost injury. That is mainly the blackening and browning of the leaves, leaf chlorosis, burning of leaf tips, floret sterility, etc., and eventually the death. The chances of damage can be minimized by adopting some management practices like adjusting the sowing time in such a way that growing season remains frost free, selection of resistant varieties, applying irrigation to the field when environmental temperature is becoming conducive to frost. Next is the effect of wind on crops. The wind profile near the crop canopy. As the wind blows over a surface, the effect of friction, which in turn depends on the characteristics of the surface, tends to slow it down to various degrees. The frictional resistance diminishes as one goes above the surface, with the result that wind speed is lowest at the surface and increases with height. For this reason, anemometers are placed at a chosen standard height, that is 10 meter in meteorology and 2 or 3 meter in agrometeorology. For the calculation of evapotranspiration, wind speed measured at 2 meter above the surface is required. To adjust the wind speed data obtained from the instruments placed at heights other than the standard height of 2 meter, a logarithmic wind speed profile above a short grass surface may be used. You can see in this equation, nu2 is equal to 4.87 divided by logarithm 67.8 nu z minus 5.42, where nu2 is the wind speed at 2 meter above the ground surface, nu z is the wind speed measured at z meter above the ground surface, where the z is the height of the measurement above ground surface. Wind can bring physiological, morphological and anatomical changes in crop plants, like it breaks petioles and twigs, thus causing reduction in flower or fruit production. It causes discoloration and abrasion on leaves and fruit from wind-blown particles. High wind causes increased carbon dioxide supply to plant through turbulent mixing, thus enhances photosynthetic capacity of the plant. Higher wind speed causes greater cuticular transpiration than stomatal transpiration. Hot dry wind has desiccating effect on plants, which may cause shriveled grains in cereal crops like rice and wheat. The wind induced damages are more prominent on sea coasts and hill slopes. Windbreaks are generally defined as any structure that reduces wind speed, whereas shelter belts are plantations usually made up of one or more rows of trees or shrubs planted in such a manner as to provide primarily some wind stress protection and also other benefits to the crop plants grown in their leeward side. So, with the help of windbreaks and shelter belts, you can reduce the effect of the wind on the crops. These are generally planted around the edges of the crop fields perpendicular to the dominant wind direction. Although the primary objective of the windbreaks and shelter belt is to reduce the mechanical damage to farm crops or the orchards, the There are some additional benefits like reduction in the evapotranspiration, improvement in the moisture balance in the soil, reduction in the soil erosion due to wind and water, and pesticide drift during spray. Trapping and conserving a uniform layer of snow on the field to protect the plants from winter frost. It promotes nesting by the insect pollinators, creating low turbulence zones for commercial insect pollinators. It improves the biodiversity. It protects the crops, pastures, livestock from cold or hot winds. It protects living and working areas from strong winds. It provides firewood, timber, fodder, honey and other products. It also provides habitat for wildlife. It also acts as fire breaks. So, thereby you can reduce the effect of wind on the crops. Next is the agrometeorological techniques. The weather-based forewarning of crop pest and diseases. Its indirect meteorological hazards like incidence of the insects, pest and plant diseases cause significant loss to the crop production. 20% of the world production was lost due to insect, pest and direct weather hazards. Hence, timely control of insect, pest and diseases is very much important. The weather parameters decide the nature, number and activity of pest and virulence of diseases, rate and duration of spread, migration of insect pests, geographical damage and the extent. Such weather factors like air temperature and humidity must have minimum, optimum and maximum values for different disease development. However, the relation between the weather parameters and plant pest disease incidence is complex as several other factors like soil moisture, soil temperature, management practices, host susceptibility, availability of carriers, primary inoculant amount etc. also play crucial roles. It can be said that for a particular disease to occur, 3 conditions need to be fulfilled. These are susceptible host plant in a vulnerable stage of growth, a disease causing pathogen in infective stage, and third is the favorable environmental condition. Temperature, humidity and wind are 3 vital environmental parameters, though solar radiation, rainfall and dew are also important in disease pest incidents. It can also be noted that extreme weather events like heavy rainfall, extreme cold and hot weather helps in controlling disease and pest. By exploring the relationship between weather, crop disease, pest occurrences and host plant relationship, agrometeorologists can forecast the disease pest risk of the crops in advance. This advanced forecasting may help in taking suitable plant protection measures such as spraying of chemicals on time. All the weather variables like air temperature, moisture, wind speed and radiation affect 4 stages like egg, larval, pupal and adult of the life cycle of all the insect pests. The increasing temperature tend to reduce the span of all stages of life cycle of cotton leaf worm, whereas the incubation period of egg and longevity decrease with respect to increase in the temperature. Soil moisture also plays a very important role in spread and distribution of soil diseases, which is caused by soil organism or soil-borne insect pest. The plant surface wetness duration, that is PSWD, is very much important in the development of insect pests and diseases. The wind speed and the direction at ground surface and at the level of troposphere helps in short distance dispersal of insect and disease spores. The high wind speed along with low relative humidity and soil moisture are very conducive for some disease development. The mechanical damage of the plants by high speed wind allows the entry of coastal organism to the plants. The light intensity and duration determines the survival of inoculum and duration of incubation period. The forecasting of disease pests using meteorological techniques was first started in 1941 in Japan. There are 2 approaches for forecasting. One is the physiological or laboratory approach. In this method, the effects of weather parameters on the life cycles of different insect pest and disease organisms are studied. The results help in setting the minimum, optimum and maximum values of the weather parameters required for a particular insect pest or disease to develop. Second approach is statistical approach. In this method, the relationship between the weather parameters and the disease and insect pest development is quantified with some statistical equation based on long-term multi-location data. For example, Prasad and Chakravarti developed a model equation for forecasting aphid population. Pt is equal to x1 pt minus 1 plus x2 T max T minus 1 plus x3 T minimum T minus 1 plus x4 T mean T minus 1, where Pt is the percent effete population. Pt minus 1 is the effete population 1 week before the observation. T max T minus 1, T min T minus 1 and T mean T minus 1 are maximum, minimum and mean temperatures 1 week before observation. The statistical relationships such as the above lead to the development of disease and insect pest forecasting models. Some disease and insect pest forecasting models are EPI-MAY, that is mainly for the maize leaf blight, NEG-FRY, that is for potato leaf blight, and BLASTEM, that is for the rice blast. Crop growth simulation models, abbreviated as CGSM. A crop growth simulation model is a dynamic simulation model that helps to estimate the crop yield as a function of weather conditions, soil conditions and choice of crop management practices. The functioning of a simulation model is represented by the block diagram given in this slide. You can see in this block diagram the input variables like site description, soil, weather, crop and management is given, that are input variable. Then various equations, it lead to various equations for describing the plant physiological processes like photosynthesis, respiration, evapotranspiration, biomass partitioning, effect of the soil, weather and management on crop growth and yield. That leads to outputs like crop growth, yield and specific management which is required. So, this shows the CGSM, or you can say these are the different elements of CSMs. Applications of CGSMs. The study on crop responses to variable sowing dates, seed rates, row spacing, irrigation schedules, fertilizer doses or schedules. Helps to identify the best package of practices such as for obtaining highest benefit cost ratio, maximum production or maximum resource use efficiency. Yield gap analysis, that is to quantify the yield gap between actual and potential yields in different climatic regions. Yield forecasting can also be done prior to harvest under expected weather. The models are used to evaluate consequences of climate change on quantity and quality of production, greenhouse emissions, etc. And also to find out the adaptation or mitigation options to counter any adverse effect. The dynamic CGSMs can be used as decision support system as part of Agromet advisory system in the country. To conclude, the agrometeorology is the study of crop, physical environment. It includes both atmosphere and soil and its interaction with biological system so that the technologies can be developed for improving the agriculture. The radiation interception and distribution within the canopy, air and soil temperature in the canopy microclimate are among the most important factors in determining the agricultural production. Agrometeorological techniques such as disease pest forewarning models and dynamic crop growth simulation models can be used to analyze and reduce risk and improving profitability of the farming community. Thank you.